This class we are going to discuss the shocks that's happening in a CD nozzle, in the diverging section of a CD nozzle. So, if you look at the CD nozzles that we have discussed, so we have a CD nozzle, and then depending on the pressure, back pressure here, we have scenarios like if I have the throat region here, when P0 is same as my PB, which is same as my P exit, there is no flow, and when I slowly decrease my back pressure, you would get a throat condition which is chalked, the chalked condition at the throat, and then in the diverging section you would get either a subsonic or a supersonic isentropic solution depending on the value of your back pressure. Okay. Now, in between, so this we call as PB critical 1 and this as PB critical 3. Okay. If you have a PB value somewhere between these two, you can expect a non-isentropic solution which involves shock. So, there is some value of PB which will create a shock inside the nozzle. For some value of PB more than P critical 3, you will have a shock somewhere outside the nozzle. Okay. So, we are going to consider that particular case where you have shocks inside the diverging section of the CD nozzle. So, if I decrease my PB to value smaller than P critical 1, say if it is if you decrease it, if your PB, say if let us take this as some value. So, I am decreasing my PB. Now, this is smaller than PB critical 1, but closer to PB critical 1, meaning the flow in the throat is chalked, okay, but it is somewhere here. Okay. So, the exit pressure is somewhere here, closer to P critical 1, the flow is still chalked. So, you will have Mach 1 here, and it is an non-isentropic solution. So, there is a shock somewhere sitting at the diverging section. So, in this condition you would have a shock that is closer to your throat. So, I have a shock that is closer to the throat which will create a shock here, which would so for some region it would be supersonic, and then suddenly it faces a shock and the pressure increases to some value here. So, this is, say, let us take it as PB 1. If I have a pressure that is still further down, and then I would have a shock that is hitting further downstream, which would go here, and if I keep on doing that, I would reach a pressure where I would have a shock sitting at the exit. Okay. So, there will be some value of PB which would create a shock at the exit, and that back pressure is your P critical 2. So, you would reach P critical 2, value of PB which creates a shock at the exit, exactly at the exit. So, this is my so called PB critical 2. So, if your pressure, back pressure is between PB critical 1 and PB critical 2, I have shock inside my nozzle. Okay. So, I have shock inside nozzle. So, we are going to discuss this scenario today. Okay. So, if your PB is between PB critical 2 and PB critical 3, then we have the overexpanded nozzle, overexpanded case, which we will discuss it later. Okay. So, earlier we had said the overexpansion is for PB somewhere between these two values. Now, we are narrowing it to this particular case where you have an overexpansion. Okay. So, this is my overexpansion, and if I reduce it further, I will have underexpansion, which again something that is happening outside the nozzle. We will discuss it later. For the time being, we are going to discuss this case. Okay. This non-isentropic case where my PB value is between PR critical 1 and PR critical 2. So, this is what we are going to discuss today. So, I would revisit the movie which we had shown in few classes back. So, this is the case where you have the PB is getting reduced and your PB is between P critical 1 and P critical 2. So, there is a shock inside the diverging section, and as soon as this shock reaches the exit, we call that as our PB critical 2. So, somewhere here, for example, in this contour, the shock has just reached the exit. So, in this case, the value of PB which creates this kind of shock, that is sitting just at the exit, is your P critical 2, and any critical pressure lower than this but more than P critical 3 is called our overexpansion. So, now you see an overexpanded jet outside the nozzle. So, if I play it further, from here on it is overexpanded. So, it is all overexpanded now, it is again overexpanded. Now, the contour, the exit is smoothly out of the nozzle. You have nice Mach number contours which are continuous. So, you have this P critical 3 now. So, any pressure between P critical 3 and P critical 2 is overexpansion, but today's class we are going to discuss the back pressures between P critical 1 and P critical 2. Okay. So, I repeat, we are going to consider this cases where you have a shock sitting inside the diverging section. So, we are trying to see again if this is a normal shock. What you see here is a normal shock with boundary layer and other interaction, because this is a viscous flow simulation and it is 3D simulation. What we are analyzing is 1D simulation, steady 1D simulation. So, there will be a standing shock that is here. So, instead of this picture, what we see will be a normal shock sitting at this location for a given PB which has been simulated. Okay. So, now we will come back to this. So, we are going to analyze this case today. Okay. So, if I have a nozzle and I have a shock here at this some location. So, let us call this as location 2, there is this entrance is location 1, location 2 I have a shock, after the location I call that as 3 and the exit is 4, sorry, and back pressure is PB. For some value of PB for a given area ratio, you have this particular case where there is a shock that is sitting inside. Now, what would be the Mach number here? What would be the exit pressure here is something that we are going to see. Okay, how do we analyze this? So, as we have done before, up to this point it is isentropic flow. Then something happens which is a non-isentropic process. Then again I have an isentropic flow. Okay. So, I will use isentropic tables to find the values up to the shock. Then we use the normal shock table to find the properties across the shock. Then we again use isentropic tables to find the shock after that. Okay. So, the best way to do this kind of analysis is to do a numerical problem and try to understand what exactly is happening. So, we will just do a numerical problem and discuss that. So, we use a combination of isentropic table and normal shock table. Question 1. So, I have a shock somewhere at the diverging section. The stagnation pressure at the inlet is 700 kilopascal and the stagnation temperature is 530 Kelvin. Area of the throat is 5 centimeter square, area of the exit is 12.5 centimeter square. Back pressure is 350 kilopascal. First, we will try to find M at the exit. Okay. That is question 1. Question 2, change in P0. M after and before the shock. Area where the shock is formed. And what is your PB for isentropic, or what is the PB for design condition? Okay. So, your A throat is given, A is given. Now, there is a shock that is formed at the shock at the diverging section implies M equals 1 at the throat, or flow is chalked at the throat, or your A throat is also your A star. Okay, that A star before the shock. So, if I use this as so inlet is 1, exit is 2, I have a shock somewhere here, I call that as X and Y. Okay. So, if it is if this statement is true, I could say A throat is my AX star. Okay. Now Ax star, we also know that P01 into A1 star equals P02 into A2 star for a non-isentropic process, which is what we have right now. Okay. But A1 star is now our Ax star. So, my P01 Ax star is my P02 into A2 star. Okay. So, what is happening here? I have an isentropic flow here just before the shock, and then I have a non-isentropic flow. After that, I have a isentropic flow. Okay. So, so if I want to find this, I divide by P02 into A2 star, or let us take it as A2. Then I do here P02 into A2 star by A2. Yeah. Okay. So P2, so instead of P02, I divide it with P2 because PB is given. PB is given. So I divide it with P2. Since flow after the shock is subsonic and isentropic, my PB2 is equal to PB, which is also my exit. 2 is my exit. Okay. 2 is my exit. So PB2 is my PB. So I can rewrite this equation as P01 into A1 star divided by PB into A2 equals P02 by P2 into A2 star by A2. Okay. So P01 we know, P01 is 700 kilopascal, PB is 350 kilopascal, A1 star is my eighth rod, which is 5 centimeter square, A2 is my A exit is 12.5 centimeter square. So this ratio P02 by P2 into A2 star by A2 is this 700 into 5 divided by 350 into 12.5, which is which is 0.8. 0.8. P02 is also your P0y, because that is your stagnation pressure after your shock, okay, and P2 is your PB, and your AY star is your A2 star, because again that is an isentropic flow after your shock. This is after my shock, okay. So P2 by P0y as my P2 by P02. And you have A2 star by A2. Now this product P02 or P2 by what is written there is P02 by P2 into A2 star by A2 equals 0.8. Now if you look at the tables, so this is a function of M2, this is a function of M2. So if I know the product, I should get my M2. So if you look at the tables, isentropic tables, for gamma equals 1.4, you have this ratio given. So this ratio is in the tables, it's the reciprocal of that. So in the tables you will see A into P by A star into P0, okay, which is our reciprocal of this. This would be 1.25. How much is 0.8? 0.8, it's 1.25. So you look at 1.25. Okay, so if you look at the tables for this particular value, your Mach number you would get it as 0.45. Okay, 0.45. So this is the Mach number that is happening at section 2, which means this is my M exit. Okay, so I have my M exit here. Okay. Now if I have my M exit, I can find P02, which is P2 into P02 by P2. This ratio is for this particular Mach number, we know the ratio from the tables again. So your P2 is now PB into P02 by P2 at M equals 2 M2. So PB is 350 kilopascal into ratio P02 by P02 by P2 for M equals 0.45. P02 by P2 would be 1 by 0.87. Okay, this would give me 402.3. Okay, so now what have you done here? So I have this shock here. Now we have found our M2, we have also found our P2, we already know our P1, we know our PB, which is also equal to our P2. Okay, and then if you know, so this is a isentropic flow. So this P02 is going to be same as P0y, which is equal to your P0y, this is same as our P0x. Okay. So, now I know P0x by P0y, which is 700 divided by P02 is 402.3. So, that is my ratio. Now, if I get that ratio, I can find mx and my. So, that ratio is how much? 1.74, and that brings the, so I take the tables, normal shock tables, I look for this particular pressure ratio, P0, okay, the inverse P0y by P0x, which is 1 by so I look at 0.57 P0y by P0x, 0.57 57 is around 2.3. So, it is around 2.3. Yes, 2.33, approximately 2.33, which also tells me the my to be 0.533 something, okay, 0.53 something. So, that is where I have my shock. Okay. So, now if I know this shock location, I also need to find the area at which the shock has been formed. Okay. So, now I know all the quantities that is required to find the area. I know my mx is mx is 2.3, my is 0.531, P0x, P0y is 402.3. So, we know now we can find our area Ax by, let us take Ax star for mx. So, what is Ax is the question. So, mx is 2.33. So, this again from the isentropic tables, 2.33 would fetch me 2.33 would fetch me a area ratio A by A star of 2.25, 2.254, 2.254. Okay. But Ax star is our A throat star, A throat, which is our A1 star, because that is an isentropic flow before from entrance to shock, okay, which is given as 5. So, my Ax is 2.254 into 5, 11.27 centimeter square. So, at this location I will have my shock. Okay. So, now what else? Now, PB at the design condition. So, the P at the design condition, that is very easy problem which we have been working on. So, you can look at the area ratio, just look at the area ratio A exit by A throat find the appropriate Mach number which will give you an isentropic flow, and that Mach number will give you the pressure ratio. So, A exit by A throat equals AE by A star equals 12.5 by 5. This will give me a Mach number at the exit, okay. A supersonic solution. So, this will have two solutions. You take the supersonic solution, which is 2.44. So, this is my design Mach number, okay. The moment I have this, I can find my pressure ratio P by P0, which is my PB by P exit by P0, which is my PB by P0. Okay. P0 is already given. Since it is an isentropic flow, P at the entrance is P0 at the entrance is going to be the stagnation pressure throughout the nozzle. So, I will have this P01, which should give me a PB value. For 45 point kilopascal, okay. You can also find the entropy change when you had the shock. So, since you know Px and Py, your P0y and P0x is e power minus delta S by R. So, you can also find your delta S. You can also find your stagnation loss this way. So, now we will do the next problem. I have a nozzle where my A exit by A throat is 2 and there is a is 3 and there is a shock sitting at some location where my area ratio is is 2. Find PE by P0 1. So, I have a P0, I have a P exit. Now, after the shock it is going to be subsonic. So, this can also be your PB. So, the pressure ratio P exit to P0, that is what we need to find. All that is given is this area ratio, nothing else. Okay. From this area ratio you have to find your static pressure, the pressure ratio PE by P exit. Okay. Again we start from the information we have. There is a shock, diverging section implies A thought is your A star 1, which is your A star. Thought is chalked. M thought is 1. So, whatever pressure you have, P01 is same as your P0x. Then it encounters a shock, you loses some of your stagnation pressure, which would be retained till the exit. Okay. Now you are given Ax by At, which is also Ax by A star. Okay. So, this is A star 1 because that is something that is happening before the shock. So, we call this as this. This is 2. So, the Mach number associated with Ax equals 2 is, I look at the shock tables, the isentropic tables, find Ax by A star 2 will give me a Mach number of Mach number of 2.2, Mach number of around 2.2. Now, the shock is happening at mx equals 2.2. So, your my equals, this is from isentropic tables. Now, my is, I look at the shock tables for Mach number 2.2, my is 1 point, my is my is 0.547. Okay. So, I have a my that is generated at this. So, your P x by P01 or P0x is Px by P01 at mx, and your Py by P0y is your Py by P02 or P0 exit at my. So, what I have written here is, I have a shock and then this is x, this is y. If that is your value, this is my P02, this is my P01, which is constant up to the shock and constant after the shock. Okay. That is one information. Second information, I can get Ay by after the shock, I have my equals 0.545, which implies my A by A star associated with this is my Ay by A2 star, Ay star or A2 star. Okay. But in the shock derivation, we have taken the control volume around the shock and we have assumed Ax equals Ay. Okay. So, this I can get it for my equals 0.74, which is, I look at the isentropic tables, I get A by A star of A by A star is 0.547, A by A star is around 1.27. Okay. Now I know my Ax, so I need to find P exit by P01, which I can rewrite it as P exit by P0 x, which is P exit into P0 y into P0 y by P0 x into P0 x by okay. So I can rewrite P0 x in this particular form. I okay. So I know this pressure ratio P exit by P01 as P exit by P0x into P exit I rewrite in this particular form. This is associated with my Mx. This is associated with my M exit if it was if there is a shock and if there is a pressure that is here. So I need to find my M exit. So if I know my M exit, I can find this ratio, and that multiplied by this should give me the pressure ratio. Now there is something okay. To find M exit, I need to find A exit by A exit star, which is nothing but what is we call it as A2 by A2 star. A2 star is also my AY star. Okay. So I need to find A2 by AY star. Which I can rewrite it as A2 by AY into AY by AY star. Which I can write it as A by A1 into A1 by AY into AY by AY star. Okay. So I need to find A exit by A exit star. So I replace this quantity in terms of quantities I know. So A2 by A1 is already given, which is A2 by A1 is A exit by A1. A1 is throat. So I will write this as my throat area. Okay, so I divide it by throat area. So A2 by A throat area and A throat area by AY and AY by AY star. So A2 by A throat area is our area ratio, which is 3, and A throat by AY is the location where your shock is happening, which is given as 2, it is 1 by 2 into AY by AY star. We already have found based on my My, which is 1.27. So this is my A exit by A exit star, which is 1.9. So your M associated with this 1.9 is look at the isentropic table. Isentropic table 1.9 the subsonic value. So, okay, we will write both. Or two point one, around 2.15. Okay. So, now we are talking about a section which is after the shock. So, the supersonic solution cannot happen there, it is always the subsonic flow. So, this is our M exit. So, your P by P0 corresponding to 0.35 is your value that has to be substituted here. So, your P exit by P01 so your P exit by P01 is P exit by P0 y into P0 y by P0 1. So, this is corresponding to m equals 0.35 which is our M exit. This is your corresponding to your Mx which is before the shock. So, these two values should give me the pressure ratio. So, m equals 3.5, my P exit by P0 is 0.918 multiplied by, I look at the shock tables, mx equals 2.2. P0 y by P0 x is 0.628, this is equals 2.2. So, this is from shock tables, this is from isentropic tables. This is around 0.756, 0.576. Okay. So, that is my P exit by P01. So, if I have this pressure ratio, I come back to the question. So, if I have that pressure ratio, P exit by P01 is 0.578, I will have shock at a location where you have this. Okay. So, if your P0 is so let us put say P exit some value, then the ratio would be this. So, your let us take P0 as say 100 kilopascal. Okay. So, your P exit is 57.8 kilopascal. Okay. So, 57 kilopascal is a region between P critical 1 and P critical 2. So, there is a shock in the diverging section. Okay. So, and that happens at a location where area ratio is 2. Okay. Okay. So, the key is you consider shock as the non-isentropic process, everywhere else it is isentropic process, and whatever be the case before and after. If I have a long duct, you do not need to have the CD nozzle information where the choking condition or throat condition is not there. but if it is a nozzle you have these conditions. Same is true for a diverging diffuser. So, if I have a diverging portion, so if I do not consider this portion and I have a diffuser and there is a shock sitting here, you do the same kind of analysis and get the tables to do the problems, the values before the shock and after the shock, and the normal shock tables for the properties across the shock, okay. And that should solve the entire shock problem, now standing normal shock problem. Okay, thank you.